Hello, everyone. Thanks uh, to all of you who joined today, to all who are looking to deepen your knowledge in DeFi, and welcome to Uniswap V4 Flash and Custom Accounting webinar. Today we will explore what these features are, how they work, and how to implement them. You can clone the repository. It is pinned in the comments. And please run Forge build and follow along with me step by step during the webinar. Short notice about me. I am Olesia Bilenka, senior smart contract auditor with 3 years of auditing experience, and my background is in software engineering with a strong focus on blockchain and security. So far, I've audited over 100 projects written in Solidity, FunC, and Rust. So the main goal of today's webinar is to understand how tokens transfers are managed in Uniswap V4. And to achieve this, we will follow a structured approach, starting with theory and then applying it in practice. Here is our plan for today. We will begin by exploring the execution flow in Uniswap V4, and this will provide the foundation to understand our next topic, which is flash accounting. And once we are confident with flash accounting, we will move on to custom accounting, which builds on that knowledge. And finally, we will look at a specific type of custom accounting, the async hook. At the end, we will have a Q&A session where you can ask any questions that might still be unclear. And if anything is confusing during the session, please feel free to ask in the chat right away so we do not lose the question. So let's get started. What are flash and custom accounting? To understand that, firstly, we need to understand how operations in Uniswap V4 are executed. In this diagram, you may see two main actors, the user contract and pool manager. The interaction may look a little bit complex, but we will break it down step by step. It all begins with a call to unlock in the pool manager, and this call enables execution of other Uniswap operation. The pool manager then calls unlock callback in the user contract, and inside unlock callback, you may include all the necessary pool manager functions like swap, modify liquidity, another swap, or so on. And after this, Uniswap V4 verifies that all tokens transfers were made correctly by both the user and Uniswap itself. And if everything checks out, the transaction is completed successfully. Let's walk through this flow step by step. For example, in the user contract, we might have a function called call unlock. And this function could have any name. What matters here is that it calls unlock in the pool manager. Here is the unlock function inside the pool manager. It unlocks the contract if it was not already unlocked, and then calls unlock callback on message sender, which is our user contract. That means your contract must implement the unlock callback, which with exactly this name. And this is the example of unlock callback, which is a custom function. Inside it, you can see the swap call and some other functions like transfer, and we will go through the next functions a bit later. And there is a swap function in the pool manager. Please notice that there is only one unlocked modifier, and this one checks whether unlock function was called first. So it is not possible to directly call this function. We should start with the unlock called as shown in the diagram. Then at the end of the transaction, control returns to unlock where final verification is performed. Please pay attention to the highlighted line in the unlock function. It checks where the number of non-zero deltas is greater than 0. If so, it means some tokens were not fully paid either by the user or by the Uniswap pool. We will examine this mechanism in details later. Also, please notice in the highlighted lines inside unlock callback, VC calls to take and settle. These functions handle token payouts, either paying the protocol or receiving owed tokens, and we will also dive into them in more details soon. But for now, let's move to the hands-on part and observe the Uniswap V4 operations flow in action. Here you can see the Uniswap V4 interaction contract, which is our user contract. It is an example. You may see that we set manager in their constructor. And we remember that everything starts with the call to unlock. So let's search for the contract where unlock is called. We have 3 calls to the unlock in the add liquidity, remove liquidity, and add liquidity and swap. So this means that there are 3 entry points into the interaction contract. But we remember that the execution flow always stays the same. So how are those operations distinguished? If we look closely, we may notice that each function builds its own data. Here, here, and here. It firstly decodes the function selector and then all the parameters. So what we do here is we create this data, which is then passed to unlock, and then this data is passed to our own unlock callback. So what we do here is we do the call to our own contract using this selector. For example, for add liquidity and swap, we will do call here, and then this function will be executed with the following parameters which were in the data, those ones. So it's up to us how we create this data, how we combine the operations, but this data parameter gives us a lot of opportunities to distinguish the operations. So let's run the test to perform add liquidity operation. You can do the same with me, or just watch how I do this. Let's clear the terminal. Forge test perform add liquidity. We need to specify match test, and we set verbosity to see the traces. Let's wait a little bit. So we see that everything succeeded, but let's review what happened here. Everything started from the call to our user contract to the add liquidity call, and this function called unlock in the pool manager. Pool manager called unlock callback inside our contract, which called add liquidity callback inside our contract as well. Then all the operations like modify liquidity, tokens transfers were made, and the transaction succeeded. Let's try to do something else. Let's try to remove the liquidity. Forge test. Let's So firstly, here we add liquidity to be able to remove it. So we will have the same traces for the add liquidity. We will not walk through them. So what we see here, we see that also the operation changed. We do the same. We call remove liquidity, then unlock function is called in the pool manager, then unlock callback is called in our contract, and unlock callback then calls our callback, inline callback, which is remove liquidity. Then modify liquidity is executed and all the token transfers are made. So the next one is a little bit more complex. Let's return to the contract. There is add liquidity and swap callback. We may notice that there is modify liquidity and swap operations here. So there are two of them. This adds a little bit more complexity. So let's try to do it. Forge test, match test. And we want to see everything which will go on there. So this test combines both adding liquidity and performing a swap in a single flow. Let's see how it is done. It all starts here. Uniswap V4 interaction contract, add liquidity and swap. Then unlock is called. Then unlock calls our unlock callback and add liquidity and swap. Then both modify liquidity and swap operations are executed. So again, regardless of how complex the logic is inside this callback, add liquidity and swap callback, the architecture ensures a predictable and auditable execution flow. However, if we look closely at our contract, we may notice that it is not secure because we are performing a lot of callbacks. So here is our unlock callback function. Unlock callback. If anyone knows what the vulnerability is here, please let me know. But let's check it. I will wait one more minute for some answer. Okay, let's run the test case. Which will show how easily our contract may be hacked. Forge test, match test. And we set verbosity. So what we do here is we create our own data and we put set manager selector here, and then we directly call unlock callback. And this should allow us to set our own contract as a manager. So here you may notice that bad address is now a manager of the contract. So to fix this vulnerability, we will need a simple line of code which will verify that message sender is a pool manager. Only manager, pool manager, can call this function. And that's it. Also, we have a lot of callbacks here, and there are already created checks here, which allows only to our own contract to call them. It is very important not to allow any external addresses to directly modify your callbacks. Let's now, with the fix, try to run the same exploit test case. And we will see if we fixed it properly. Something went wrong here. I'm sorry. Let's check it again. Oh, that's fixed to the wrong contract. Okay, let's implement it here. Unlock callback. Yeah, here we don't have this verification, so let's copy paste it from here and paste it here. And now we fail with only pool manager can call this function. So with just one simple line of code, we avoided critical vulnerability. So let's move on to even to the next topic. And please let's think how before Uniswap V4 in the previous Uniswap versions token transfers were made. For each operation, each individual immediate token transfer was required. For every swap, every add liquidity or remove liquidity had to handle payment immediately, which made complex operations harder and more gas intensive. And Uniswap V4 introduces a simplified model, and now we will see how it works. And this is called flash accounting. This is the next topic in our agenda, and it is based on the knowledge we just obtained. So imagine an unlock callback with both swap and add liquidity call. So just like in our previous example, first, the swap is executed. For example, user wants to add wants to swap 100 token A to 80 token B. Delta A becomes minus 100. That means that user contract owes 100 token A to the pool manager, and delta B becomes 80, which means that pool manager owes 80 token B to the user contract. This makes non-zero delta count equal to 2 because we have two tokens with non-zero deltas, token A and token B. Then inside the same unlock callback function, we add liquidity. We add 30 token B and 20 token C. Token A delta remains the same because we do not modify it. Token B delta becomes less because user wants to pay 20 tokens, which makes the delta lower. And token C delta becomes minus 20, which means that user has to pay 20 tokens to the pool manager. This makes non-zero delta count equal to 3 because we already have non-zero deltas for token A and token B, and only token C has changed. If we return to our execution flow diagram again, we may notice in the unlock function that there is a non-zero delta count verification. In case it is not equal to 0, the transaction reverts. So in our case, this non-zero delta count is equal to 3. So this check would fail and revert in case we finalize the transaction here, and that's correct because no tokens have been transferred yet. So what we need to do now is we need to make this value equal to 0. So first of all, user contract transfers the tokens it owes, 100 token A and 20 token C. And also, after that, it calls settle in the pool manager. Settle function checks all the tokens, all the currencies updates, and in case everything is paid correctly, it would set those deltas for token A and token C to 0. This will make non-zero delta count equal to 1 because token A and token C delta are now 0, and only token B is not 0. So what we need to do now, user contract needs to call take on the pool manager. This will make user contract receive those 20 token B that pool manager owes to it. And after this, delta for token B becomes 0. And which means that all deltas are settled. And now we see that non-zero delta count is equal to 0, and this verification will succeed and the transaction will be completed successfully. Let's move to the hands-on section and try to settle deltas ourselves. Yes. We now switch to a new contract, which is fully identical to the one we reviewed before, except for the one thing. It doesn't implement any logic for settling or taking tokens. For example, add liquidity callback, we only modify liquidity and then we do nothing. So let's try to run the test case, the same test case for this function. Forge test match test, and we want to see everything. So again, we execute absolutely the same test case. But we get the following error: currency not settled. This happens because the token that contract owes to the pool manager has not been transferred and settled. So we tried to add liquidity, we changed the delta, but we didn't pay anything. So we need to fix this. To fix this, let's implement an internal utility function. Function, let's call it transfer and settle. We will accept currency as a token which we want to pay, address of user from which we will transfer the tokens, and amount to transfer. Amount. So yeah, now and this one should be internal. Please notice that I will not use safe transfer here, just for make it as simple as possible, but for the production, we always recommend to use safe transfer library. So what we do here is we do unwrapping of the currency to make it applicable to your C20. Currency, currency unwrap, currency. Then we perform transfer from user to our contract. Transfers this, and in this amount, which we will specify later. What we do next? We need to approve those tokens to the pool manager, because when we will call the next function, the pool manager will need this approval from our contract. So what we do here is we approve pool manager amount. And the final step is to call the created by Uniswap function currency, which is called settle. We pass pool manager here. Payer is address this, because the payer is not user, already because user transferred tokens here, and now this contract is the contract which will pay those tokens. That's why we have approved them. And amount is amount we will specify, and burn false. It is out of today's topic. And now we need to integrate this function into our callback. This is our callback. First of all, we need to understand how many tokens we need to pay. For this, we already have the returned delta parameter, which may allow us to retrieve those amounts. Amount 0, delta, amount 0. But because we owe tokens to the pool manager, this delta is negative. So to make the positive amount to settle, we need to make this negative value negative again. So what we need to do here is to set minus and to do some casting here. And then and the same for the second token. Then all we need to do is to call our internal function key currency 0 from we have clear as a parameter, amount 0, and the same for the second token, currency 1, amount 1. Let's try to run our test case again. And now we see that liquidity is successfully added to the pool, and there are no currencies not settled errors with just these two simple internal function calls. So let's try to do the next operation. Let's try to remove liquidity. Again, we perform exactly the same test case as in previous part. Forge test, match test, and let's trace back everything here. We may already predict what will happen, and yes, now we again obtain currency non-settled error, but this time the problem is a little bit different because now we want to remove the liquidity, and it means that the protocol owes tokens to our contract, not the way around. So since Uniswap or pool manager needs to pay to us, we cannot use the same function we created. We need to create another function, internal utility. Let's do it. Function. Let's call it take and transfer to clear. It will again accept currency, address 2, that's where tokens will be paid to, and amount of tokens. And this should be internal. What we do here is we just call currency, take, we specify the pool manager address here, we mention where we want these tokens to be transferred to and the amount of those tokens, and false as burning, which is also out of topic. So what is important to understand here is that we cannot just call take and pool manager will recalculate and return everything for us, we need to set this amount, and this amount should be exactly equal to the one that pool manager owes to us. So let's now integrate this into our callback. Here is remove liquidity callback. Again, we need to obtain amounts. Let's copy paste it from here. But now those deltas are positive because it means here that pool owes tokens to us. So we do not need to do this here. And then we need to call our function key currency 0, clear amount 0, and the same for the second token. Let's try to run the test case again, and we will see if we have fixed the delta settlement. And now we see that we successfully removed the liquidity and there are no currency not settled errors with just 2 calls to take calls. So if you remember, the next example will be a little bit more complex because it will contain modify liquidity and swap in one transaction. But the good news are we already have all the utility functions for it. We will just need to implement them properly. But let's try to run this function and we will see. We already may predict what will happen, but let's see. And we again obtain currency not settled error. And now all we need to do is we need to handle those 2 deltas. To do it transparent, let's do it one by one. Let's firstly handle the liquidity delta. So as we remember, in case delta is negative, it means that we owe something to the pool, and in case it is positive, it means that pool owes something to us. So let's check the delta for the first token. Liquidity delta result. If liquidity delta result amount 0 is less than 0, let's obtain this value. We will need this line. We will need here again make negative of negative to obtain it as positive. And we need to call transfer and settle. Key currency 0, clear amount 0, and else if we do not need else if in case because this function is only for add liquidity, the delta may not be positive here. So all we need to do here is we need to check the same for the second token. We just replace 0 to 1 everywhere. And that's it. We settled deltas for the liquidity delta. We may try to run the test case again. But we still get the same error. And this happens because we have done nothing with swap delta. So to handle swap delta, we need to understand that we may either owe tokens or to be owed tokens. So here we need to check all the cases. So if swap delta amount 0 is less than 0, we do the same. We make this value positive and we call transfer and settle. Else if this swap delta amount 0 is bigger than 0, this means that pool needs to pay these tokens to us. So what we need to do here is we need to obtain this delta. So it will be amount 0, and we do not need to make it negative because it is positive already. And we need to call take and transfer to clear key currency 0, clear amount 0. So that's it for the first token. It will be either this or this, depending on the order of swap. So now we need to handle the second token, and this will be the same. We just need to replace 0 to 1 everywhere again. You may notice that we are using a lot of if-else logic here, and we could refactor this into a more elegant way, into a more generalized way, but the purpose of this webinar is to make everything as simple as possible. And once you are comfortable with deltas, you may refactor this and to make it much more clearer and much more generalized. So what we've done here, firstly, we checked if we owe any of tokens when we were adding liquidity. Then we checked if we owe first token to the pool during the swap to the pool, or it owes to us, and we did the same for the second token. Let's try to run this huge test case again. Yeah, and now we see that everything, that the transaction succeeded, and the liquidity was added and the swap was executed, and just with those simple lines of code. So all we need to understand is how this transfer and settle works and how this take and transfer to clear works. And once you're comfortable with those functions, you may do a lot of delta settings, a lot of your custom implementations of user contracts. So just need to do some practice using such simple examples. But now this concludes our deep dive into Flash accounting. We've seen how Uniswap V4 lets us to defer all token transfers until the very end of the transaction using deltas. And now let's move on to something even more powerful, which is called custom accounting using hooks. Here is our familiar Uniswap V4 execution flow again. But as many of you may already know, Uniswap V4 introduces a new concept, which is hooks. Hooks are the calls to your own smart contracts that can be triggered at specific moment during the execution based on how you configure the pool. Hooks may do a lot of own behavior, but what is important to us today is that they can modify deltas. So there is a full flow execution with hook. We see that there is a third actor with which is hook, and this is the swap example. We see that pool manager before the swap it calls before swap hook, and after the swap it calls after swap. And these hooks can contain any logic, and what is most importantly for us, they can modify deltas before the transaction completes. And this mechanism is called custom accounting. Let's see some example. For example, user modifies liquidity by adding 110 token A and 80 token B. The pool has and the pool then has configured before add liquidity hook. So hook wants, for example, to take 10% of fees from token A and to add extra 30 tokens B to the swap, to the liquidity modification. So what hook needs to do? They need to return U deltas, -11 for token A, which will mean that pool owes 11 token to the hook and 30 tokens, 30 for token B, which will mean that hook owes 30 tokens to the pool manager. Also, hook needs to call the same functions, for example, take, to receive 11 token A as a fee, and this will decrease the non-zero delta count because the delta will be paid. And also hook needs to call settle, and firstly it needs to call transfer 30 tokens B and then call settle, just like in the example we did before. And this will also decrease the non-zero delta count. So for both, for user contract and the hook, this non-zero delta count is the same variable. So in case you implement your custom hook, it will also impact this non-zero delta count, and in case hook modifies delta and doesn't settle it, the transaction won't succeed. What is important to understand here is the deltas are from perspective of hook. For example, if hook wants to take a fee, the delta must be negative. And in case hook wants to add some token, it returns a positive delta. So this is the foundation of custom accounting. Let's review some practical example. Here is a basic hook contract using get hook permissions. It has before swap set to true and also before swap return delta set to true, because in case we want to modify delta, we need to also specify this to true. What we want to do here, we may see that this hook returns zeros and it does nothing. But for example, we want to implement a hook which will take 10% of amounts to swap when the amount in is specified. So here, in case amount specified is less than 0, it means that there is a specified amount in. So we will need to handle this. Let's try to run the test case. Hook fee test. So here we are trying to swap 100 tokens, and we want our hook to receive 10 tokens. Match test, and let's see. what will happen. And for sure, it is failed because our hook has 0 tokens because we haven't implemented any functionality here yet. But let's do that. First of all, we need to understand their order of swap. For this, we may use specified. We may use the parameter 0 for 1 from Uniswap. In case it is true, the specified currency is currency 0, and otherwise it is currency 1. It is very important to understand which currency is specified because the order of the deltas we return should be strict. Firstly, we return the delta for specified token, and the second value is for unspecified. It's not like for token 0, token and token 1. We always need to understand which amount is specified. So when we have this, we may receive the amount of tokens. Specified amount. What we do here, we may get params amount specified. But as we remember, in case user needs to pay to the pool manager, this value is negative. So we need to make it negative again to make it positive. And all we need to do now is we need to calculate the fee. We already have the internal function implemented, which will calculate 10% of our swap amount. Fees, calculate fee, specified amount. Now we have this fee, and we will do the same as we did in there when we were setting deltas. We will call take because we want to take this fee from the pool manager. Manager. Recipient is address this because we want to store fees in the hook contract. We set the amount, and this is false. This is not needed for us for now. Let's try to run the test case again. And we receive the familiar error, currency not settled. However, we called take function, so what was wrong? The wrong was this line because we returned 0 delta. However, we took this fee. So in order to make this settled, we need to return the correct value here. For this, we may use the already created by Uniswap function to before swap delta. Delta specified is fee. We need to do this. And delta unspecified is 0. We do nothing with this. And yeah, let's try to run our swap with hook again. And we see that now everything passes and our hook obtained 10 tokens. So let's go on to the theoretical part again. Because it is important to understand that delta settlement can occur in different orders during the execution of a single transaction. However, this flexibility also comes with risks. When designing this order in which we settle deltas, we must take the current state of the pool into account. If we settle deltas in the wrong order, it may lead to underflows or other unintended side effects. For example, in case we want to take a fee, we need to be sure that pool already has those tokens. So it is better to take fees after swap. But this is only one example. So though Uniswap doesn't prohibit any order of delta settlement when designing our systems or when auditing them, we need to review whether this order is secure and whether this will not lead to unintended side effects. So finally, let's take a look at async hooks. Async hooks are built on top of the custom accounting approach, which we just implemented in our hook. They are called async because they bypass the pool manager logic entirely. Instead of relying on it to manage the token transfers, the hook itself takes full control. In practice, this means that the hook captures the entire amount specified for itself. So async hook is only possible for the V4 swap hook, which has amount specified, just like the one we just implemented. Let's implement this in the code. To do this, all we need to do is we need to change the percentages here, and now our fee is 100 percentages, which is full amount specified. And let's expect to receive everything to our hook instead of pool manager. And we see that our hook received 100 tokens, which means that async hooks give us a lot of flexibility as well as custom accounting. But with that power comes a lot of responsibility because async hooks bypass the core protocol logic and the surface for vulnerabilities increases significantly. In other words, async hooks are powerful, but must be used with great caution. There is a QR code on the screen that links to the article Mastering Transient Storage in Uniswap V4, and I encourage you to scan it and bookmark it for later reading. The deltas we were talking today about are stored in this storage, and if you would like to explore this topic even in more depth, including detailed gas cost calculations, please feel free to check out this article. Also, a quick note about Hacken. We provide full spectrum cybersecurity services covering everything from smart contracts audits to on-chain monitoring, penetration testing, L1 audits. And if you are interested in learning more or want to explore how we can help secure your project, feel free to book a direct call with Vladi. He will walk you through all the details and answer any questions you have. Also, feel free to ask any technical question or questions about our services in the chat. We'll be more than happy to answer them. In case there are no questions, I think that we may wrap up the webinar. And there is a question, what's the need of unlock if it's always allowed? I'm not totally sure that I got your question, but unlock is needed because when we call unlock, we then can call all the other operations, and during this execution of unlock, we have those deltas which are stored in transient storage, and they are not zero. So if in case we call unlock, we specify this transaction execution. So it is because now we may do a lot of operations in one transaction, and we need to group them somehow. And this unlock allows us to group them. Did I answer your question? Unlock will fail in case it is already unlocked. So it is like a reentrancy modifier. It doesn't allow to call itself. And it will fail when calling it. Also, unlock will fail in case deltas are not settled. So in case non-zero delta count is not equal to 0. So there are two checks. The first one, it checks whether it hasn't been called yet, and the second, if everything is settled. Cool. You're welcome. Cool. Thank you a lot for your attention. And I believe that's not questions which I can answer. I'm not sure if there is someone from Hacken who can answer when high token will be on Binance. Yeah, we will forward this question to the people who work with this. So if there are no questions about Uniswap, we can finalize the webinar. Thanks again, everyone who joined and listened to me. And again, in case you're interested in any cybersecurity services, feel free to contact with the Vladi. You may scan this link here. Have a good day. Bye.